right now, in this exact, millisecond, the device you're using to listen to my voice is basically screaming into the digital void.
It really is. It's firing off just dozens, maybe hundreds of these invisible demands.
Yeah, exactly. High-speed demand shooting all across the globe. Like, it's negotiating with fiber optic cables buried under oceans, pinging these massive warehouses full of flashing lights in completely different time zones.
And routing encrypted packets of data through the air, right?
Right. And the crazy part is you don't notice a single bit of it.
Because the illusion of the modern internet is tranquility. I mean, we've basically engineered the chaos entirely out of the user's view.
It's a brilliant deception, honestly. We tend to think of the internet as this like magical floating cloud, where information just sort of exists.
Right, like you click a link and poof, a web page just magically appears.
Exactly. But the reality is much more industrial than that. It's closer to sitting in a really exclusive restaurant.
Oh, I like that analogy.
Yeah. So imagine you sit down in this quiet dining room, nice ambient lighting, and you point at a menu. And then, 20 minutes later, a perfectly seared scallop just arrives at your table.
Right, but you never actually see the reality of that scallop.
Exactly.
You don't see the head chef screaming, the grease fires, all that intense orchestrated chaos happening literally just a few feet away, right behind those swinging kitchen doors.
Exactly. And today, we are kicking those swinging kitchen doors wide open. So welcome to the deep dive.
We have a really massive stack of notes today.
We do, and it's drawn from the world of web systems architecture. It's this fascinating look at the actual plumbing of the digital world.
And the source material we're working from today actually happens to be rooted in Brazilian tech documentation.
Yeah, which is super cool because we're going to unpack some really interesting global perspectives on this stuff.
So what's our specific mission here?
Well, our mission is highly specific. We are going to decode something called the client-server model.
Right.
And we are going to do it in a way that even if you have, never written a single line of code in your entire life, you are going to understand the mechanics of exactly what happens behind the glass of your screen.
Because to truly grasp the gravity of this architecture,
Yeah.
We really have to look at the friction that forced it into existence in the first place.
Right. It didn't just appear out of nowhere.
No, not at all. We are going to trace a lineage all the way from these massive, freezing cold mainframe rooms of the 1970s.
Oh, man, the 70s.
Yeah, where human beings literally had to physically wait in line to use a computer.
Which sounds insane now.
It does, and we'll trace that all the way to the hyper-responsive, decentralized web that you're literally carrying in your pocket right now.
Right, and we won't just list what these technologies are, because that's boring. We have to look at the catastrophic failures, and honestly, the sheer human frustration that made developers invent better ways for machines to talk to each other. So I want to start by just anchoring us to that core concept. The phrase client-server model gets thrown around a lot, right?
Everywhere, yeah.
So let's define the actual players. If we stick to our restaurant environment, the client is you. You are the patron.
Right.
You are sitting at the table, looking at the menu, and you are initiating the interaction. You're the one placing the order.
And that initiation, that is the defining technical characteristic here.
Okay, break that down for me.
Well, in our digital reality, a client is basically a user on a device. So your smartphone, your tablet, your laptop.
Okay.
The client always starts the conversation. It says, hey, I need to view this specific news article, or I need to verify my bank balance.
So it fires off a request.
Yes, it fires off a request, and then its primary job is literally just to wait.
Huh.
It has a definitive start and a definitive end to its workflow.
Right. Okay. And so the server is the kitchen. It doesn't initiate anything, right? It just waits for orders to come in.
Exactly. It exists in a relentless state of waiting.
Relentless waiting. I love that.
Yeah. I mean, a server is a highly powerful, dedicated machine. Usually it's sitting in some climate-controlled data center somewhere.
Just whirring away.
Right. And it never sleeps. Its entire existence just revolves around listening for requests, processing them, gathering the requested ingredients from a database somewhere, and then formatting a digestible response to send back to the client.
So the client asks, the server provides.
You got it. That request and response cycle is basically the fundamental heartbeat of the entire global internet.
But the internet wasn't born this way?
No, definitely not.
The separation of duties, like the diner out front and the kitchen in the back, that actually had to be invented.
Right.
And the notes point us back to the 1970s for this, specifically to Xerox PRX.
The Palo Alto Research Center. Legendary place.
Yeah. But why did they have to invent this? Like, what were we doing before the 70s?
Well, before this, we were suffering under what is known as the centralized model. So picture a big corporation in the late 1960s that would have one massive room-sized computer.
The mainframe.
Exactly, the mainframe. And that single machine was basically a dictator. It did absolutely everything.
Everything.
Everything. It held all the data on these massive tape drives, and it performed all the computational thinking.
So how did a regular employee actually, get any work done? You couldn't exactly put a room-sized mainframe on your desk in a cubicle.
No, you couldn't. So you used what was literally called a dumb terminal.
A dumb terminal. That sounds insulting.
I mean, it was just accurate. It was literally just a keyboard and a cathode ray tube screen, and it was wired directly through the walls of the building to the mainframe.
Okay, so just a screen and a keyboard.
Right. And the terminal itself did zero processing. It had no brain of its own.
Wow.
So when you pressed the letter A on your keyboard, that physical keystroke had to travel down a long wire to the mainframe. Yeah. The mainframe thought about it, decided to display an A, and then send a signal back down the wire just to light up the pixels on your screen.
That sounds incredibly fragile. Like if that one central brain goes offline,
The entire company just ceases to function.
every screen goes dark.
Every single one.
Yeah.
Furthermore, if, say, too many people were typing at the exact same time,
Oh, I can see where this is going.
the mainframe would get completely overwhelmed trying to process hundreds of individual keystrokes from all over the building.
Right?
And the entire system would just slow to an absolute crawl. It was basically an unscalable bottleneck.
Okay, so the researchers at Xerox PageArc realized that this dictator model was dead. They needed to distribute the power.
Exactly. They decoupled the data from the processing.
Okay.
The core philosophy of the client-server model is that the device sitting on your desk should have its own brain.
It should be able to do its own thinking.
Yes. And it should only bother the central computer when it absolutely needs a specific piece of shared information.
So our sources outline a really practical example of how this looks in a standard internal company network, like a local area network, a LAN.
Right, let's look at that.
So let's say you're an architect working in an office. You have a powerful desktop computer on your desk. That is your client machine.
Okay.
It uses its own internal processor to run your really heavy CAD software, and render your 3D graphics locally.
Right. And meanwhile, sitting in a secure closet down the hall is a rack of specialized servers.
And they aren't trying to run your design software.
Not at all. Instead, you have one machine that is dedicated exclusively to storing the firm's shared blueprints. That's the file server.
Okay, makes sense.
And then you have another machine whose sole existence is just routing the company's internal communication, the email server.
So by splitting the labor like that, the whole network can finally breathe.
Exactly.
Your desktop handles your screen and your software, and it only whispers to the server room down the hall when you click Save to Network Drive.
The efficiency gains were monumental,
Right.
truly. But, human ingenuity rarely just stops at good enough.
No, it really doesn't.
Once software developers realized the sheer power of physically separating the interface from the data, they started wondering, how far can we slice this architecture?
And that leads us directly into the evolution of tiers.
Right.
Our Brazilian source material actually refers to these as camadas, or layers. And reading through this history, I gotta say, it feels less like a smooth technological evolution and more like a series of desperate escapes from IT nightmares.
Desperate escapes is honestly the perfect framing for this.
It really is.
Let's look at the first iteration of this.
Yeah.
The two-tier architecture.
Okay.
On paper, it sounds perfectly logical, right? Tier 1 is the client machine sitting on the user's desk. Tier 2 is the database server sitting in the back room.
Okay, so what is the client actually doing in this two-tier setup?
Well, the client computer is handling the user interface. So the buttons, the text, the screens you look at.
Right.
But crucially, it is also handling the business logic.
Okay, let's define business logic real quick because that definitely sounds like corporate jargon.
Fair enough. Think of business logic as the actual rules and the math of the application itself.
Okay, give me an example.
So, if the company is running payroll software, the specific rules dictating overtime pay, the current federal tax brackets, and the logic for deducting health insurance, all of that lives inside the software that is installed directly on the user's desktop computer.
Oh, wow, okay.
Yeah. And the database server in the back room. It's literally just acting as a dumb storage locker.
Just holding the numbers.
Right. The client pulls the raw numbers out of the locker, runs all of the complex tax math locally on the desktop processor, and then just shoves the finished paycheck data back into the locker.
Okay, I can immediately see the catastrophic flaw in that design.
Oh, yeah.
Yeah. Like, what happens on January 1st when the government suddenly changes the federal tax rate from 12% to 14%?
You have an absolute IT disaster on your hands.
Right.
Because the business logic, the actual math formula lives on the client computers. You cannot just update the central database.
You literally have to send an IT professional running from desk to desk
Yep.
across a massive corporate campus with a huge stack of floppy disks or CD-ROMs, manually uninstalling the old software and reinstalling the new software on every single machine.
It was brutal. And if you have 5,000 employees, that is 5,000 manual updates.
And if that IT worker accidentally misses just one computer?
Then Bob in accounting spends the next 6 months calculating taxes using the wrong federal bracket,
Oh, man.
which exposes the entire corporation to massive legal liability.
Yeah, that's bad.
Very bad. The two-tier model was basically a logistical nightmare for maintenance and version control. The friction was just unsustainable.
So how do you eliminate the floppy disk? How do you fix that?
You add another layer. You invent the three-tier architecture.
Oh.
This is where we see a truly monumental paradigm shift in software design. Developers realized that the business logic could not live on the client's desk. It was way too volatile.
So they inserted a new layer right in the middle,
Exactly.
the application server.
You got it. Tier 1 is the client, Tier 2 is the application server, Tier 3 is the data server.
Okay, so walk me through how Bob's computer behaves now in this new setup. What is actually installed on his physical machine?
Nothing but a web browser.
Just a browser.
Just a browser. This is the absolute genius of the three-tier system. The heavy, complex payroll software is completely removed from the user's desktop.
Oh, that is so much cleaner.
It really is. The user interface, the visual buttons and the forms, those are generated centrally.
Right.
The complex tax math and business rules now live exclusively on the application server. And the raw data still lives on the data server.
Okay, so let me visualize this. Bob opens Google Chrome, types in an internal web address, and the application server sends him a web page. He types in an employee's hours and clicks Submit. That data travels to the application server, which does the new 14% tax math, saves it to the database, and then sends Bob a web page showing the result.
Exactly. And the beauty of this is centralized management.
Right, because of the updates.
Yes. When the tax rate changes again next year, the IT department doesn't run around the building sweating.
No more floppy disks.
No more floppy disks.
Yeah.
They log into the one single application server, change one line of code from 14 to 15, and hit save.
And that's it.
That's it. Instantly, simultaneously, all 5,000 employees across the company are using the updated math the very next time they refresh their browser.
That is incredible. It turned the web browser into this, universal window.
It really did.
You don't need to care if Bob is using a Mac, a Windows PC, or even an iPad. As long as he has a browser, he can access the logic.
Exactly.
But looking at the outline, the notes mention that modern systems usually run on a 4-tier or N-tier architecture.
Yes, they do.
Why slice the cake again? Isn't 3 tiers enough? What is a 4th tier actually doing?
So in a three-tier model, the machine handling the business logic and the machine physically serving the web pages to the browser are often the exact same entity.
Okay.
A 4-tier architecture violently separates them for the sake of security and massive scalability.
How does separating them make it more secure, though?
Well, imagine you run a massive e-commerce platform, you launch a huge marketing campaign, and suddenly 2 million people try to hit your homepage at the exact same second.
Oh, wow. Okay.
Your web server, the machine responsible just for displaying the storefront, gets completely overwhelmed by the traffic and crashes.
Right, a classic denial of service scenario.
Exactly. But because your architecture is N-tier, your application server,
The one handling the credit cards?
right, the one handling the credit card processing logic, and your database server, which holds all the customer data,
Okay.
they are physically isolated on entirely different machines, hidden deep behind firewalls.
Oh, I see.
The public internet cannot even talk to them directly. So the web server might crash, taking your storefront offline, but your core data vault remains completely untouched and perfectly secure from the traffic spike.
It's like putting your reception desk out in the lobby, completely separate from the actual vault down in the basement.
That's a great way to look at it.
If a mob rushes the lobby, the vault is still perfectly safe.
Exactly. And it also allows you to scale surgically.
What do you mean by surgically?
If your database is running slowly, You don't need to upgrade the whole system. You just add more RAM specifically to the database tier.
Oh, that's smart.
This physical isolation is exactly why you can pick up a brand new, out-of-the-box smartphone, open Safari, and immediately access a sprawling corporate CRM or edit a 4K video in the cloud.
Right, because your tiny phone is just rendering the presentation layer.
Yes. Massive server farms in Virginia or Ireland are doing the actual computational sweating.
But this introduces a massive logistical hurdle, doesn't it?
How so?
Well, we have a client in Tokyo, a web server in London, an application server in New York, and a database in Ohio. How do they actually orchestrate this conversation?
I see what you're saying.
If they are built by completely different companies using different hardware, how do they all speak the same language?
Well, they rely on a universal, strictly enforced protocol. For the World Wide Web, that fundamental rulebook is HTTP.
Hypertext Transfer Protocol.
Right.
Our sources emphasize HTTP as the absolute backbone of the web. But what is it physically doing?
HTTP is basically a communication protocol that dictates the exact syntax of the request and response cycle.
Okay.
It is a stateless, text-based language. When you click a link, HTTP dictates exactly how your browser must format its request.
So it has to be polite.
Well, it has to be structured.
Mm.
It must state exactly what it wants, what browser it is currently using, and what formats it can accept in return.
The notes actually provide a really concrete example of this cycle.
Let's hear it.
Let's say you are browsing an electronics store on your phone, right? And you decide you want to look at a list of televisions.
Okay.
You tap the Show TVs button.
Right. And that physical tap on the glass of your phone is instantly translated into an HTTP request.
Okay.
The client formats a message that essentially says, I am requesting the resource located at lister-tv.php. I am a mobile browser. Please respond.
And that request shoots through the air to a cell tower,
Yep.
down into a fiber optic cable across the country, and hits the web server hosting the store.
Exactly. And the server reads that HTTP request. It says, okay, the client wants lister-tv.php.
So it turns into the kitchen.
Right. The server turns around, talks to the database, pulls the current prices and images for every single TV currently in stock, and constructs a brand new response file.
And the notes call this resulting file listigem-tv.php.
Perfect. So the server then packages that file with an HTTP response header.
What's in the header?
This header contains a crucial piece of information,
Mm-hmm.
a status code. It says 200 OK, which basically means, I found what you asked for, here it is.
Nice.
It fires the package back across the globe, your phone receives it, reads the HTML, and suddenly a grid of shiny televisions just materializes on your screen.
And that entire transatlantic conversation took, what, maybe 200 milliseconds?
Barely a blink of an eye.
It's wild. And HTTP is famously startless, right?
Yes, very important point.
Meaning, once the server sends the TVs, it completely forgets who you are. The transaction is just over.
Right.
If you click on a specific TV a second later, the server treats you like a brand new stranger just walking in the door.
Precisely. And that statelessness keeps the server incredibly fast.
Because it's not wasting memory.
Exactly. It doesn't have to waste memory trying to remember millions of active users and what they were just doing.
Right. But there is a really fascinating evolution regarding how this cycle is initiated.
Oh.
Well, the absolute golden rule of the client-server model has always been, the client asks, the server answers.
Right. The server never speaks unless spoken to.
Exactly. But that rule isn't entirely true anymore, is it?
What do you mean?
What about push notifications?
Yes.
I mean, I can leave my phone sitting on the table completely untouched, and suddenly it buzzes with a breaking news alert.
Yeah.
I didn't initiate a request. My client didn't ask for the news, so how on earth did the server know to send it?
You are touching on a critical architectural workaround known as a push-as service.
Okay.
Historically, if an app wanted to know if there was breaking news, it had to use a method called polling.
Polling, like asking a question.
Basically like a kid in the backseat of a car on a road trip. Are we there yet? Are we there yet? Is there news yet?
Oh, God.
Exactly. The phone would wake up every 30 seconds, send an HTTP request to the server, ask for news, get a no, and go back to sleep.
That sounds exhausting.
It was disastrous for battery life and created an immense amount of useless empty traffic on the server.
So how does push fix the battery drain?
By inverting the relationship entirely. When you install a news app and agree to notifications, the client initiates a connection. But instead of hanging up, it leaves a tiny low-energy socket permanently open to a specialized push server.
A permanently open pipe.
Exactly. It essentially tells the server, here is my exact address. I am going to sleep now. If something explodes in the real world, you have permission to initiate the conversation and push the data down this open pipe.
That is brilliant. The server becomes the active participant, saving the client from exhausting itself by constantly asking.
It really is an elegant solution.
Okay, so we've mapped out the invisible data pipes. We know how the information travels back and forth.
Right.
But data in its raw HTTP format is literally just walls of text and code.
Oh, it's completely illegible to a normal human being.
Exactly. The server's perfect response is entirely useless if the human client can't actually make sense of it on their screen.
And this brings us to a massive, often underappreciated discipline in tech, human-computer interaction, or HCI. The interface is the critical bridge. In the early era of computing, developers honestly didn't care about interfaces.
They just used command lines, right?
Yes, just a black screen and a blinking green cursor.
It's so intimidating.
If you wanted the computer to move a file, you had to memorize a really rigid, obscure syntax of text commands.
Right.
The philosophy is basically, the computer is very expensive, the human is very cheap, therefore the human must adapt to speak the machine's language.
Wow. But as computing moved out from, university labs to living rooms and corporate desks, that philosophy completely failed.
It had to.
You can't expect a CEO or a casual shopper to learn complex syntax just to read an email.
Exactly. The burden of translation had to shift from the human back to the machine.
Makes sense.
So we evolved to graphical user interfaces, GUIs.
Right, the stuff we use today.
Yes. The entire goal of modern HCI is to hide the brutal complexity of the underlying database and present a logical, intuitive, visual path for the user. We use metaphors. Folders, trash cans, buttons, things that make sense in the physical world.
But building those visual interfaces today introduces what I imagine is the single biggest nightmare for a front-end developer.
Oh, I know what you're going to say.
The screen size problem.
It is a dizzying logistical challenge. Truly. Our source material cites data highlighting the sheer fragmentation of the hardware market right now.
I mean, think about the reality of the web right now.
Yeah.
You have someone on a crowded subway looking at a website on a budget smartphone from, 5 years ago with a tiny screen resolution of 360 by 640 pixels.
Okay.
At the exact same second, a graphic designer is looking at that exact same website on an ultra-wide, curved desktop monitor running 4K resolution.
It's true.
How is it physically possible to design one website that works perfectly on both a smartwatch and a jumbotron?
Well, in the early days of mobile internet, the industry's answer was a rather blunt force concept called adaptive design.
Which basically means, why not just build a bunch of different versions?
Pretty much. Let's make a small website for phones, a medium one for tablets, and a big one for desktops.
Right.
That is precisely what adaptive design is. It relies on fixed, static layouts with hard-coded breakpoints.
Okay, so how did that work in practice?
The development team would literally design and code 6 distinct versions of the website.
6 versions?
Yeah. And when a user clicked a link, the server would instantly measure their screen size. It would say, you have a 700 pixel widescreen. I will serve you the 720 pixel layout because you aren't quite big enough for the 1024 pixel layout.
Wait, but if I have a 700 pixel screen and you serve me a layout designed for 720 pixels,
Yeah.
I have to scroll sideways just to read the text.
Exactly.
And if you serve me a 360 pixel layout, half of my screen is just empty, wasted space.
Right.
Plus, forcing a team to update 6 different versions of a website every single time you want to fix a typo, that sounds maddening.
It was wildly inefficient. It was a static, rigid solution applied to a highly dynamic problem. The industry had to evolve, and they moved to the modern standard.
Which is?
Responsive design. And the philosophical origin of this is actually rooted in physical, brick-and-mortar architecture.
Wait, really? Like building design?
Yes, there was a movement in physical architecture concerning spaces that dynamically adapt to the people using them.
Oh, cool.
Using sensors, robotics, and flexible materials, a room might physically expand its walls or adjust its lighting based on the density of the crowd.
That's amazing.
Web designers adopted this exact ethos. They realized that a web page shouldn't be a rigid painting. It should be a fluid container.
Okay, so how does responsive design achieve that fluidity in the actual code?
It abandons the concept of fixed pixels entirely.
Entirely.
In the old days, you would tell an image, you must be exactly 400 pixels wide.
Right.
In responsive design, you use relative math. You tell the image you must always take up exactly 50% of the screen, regardless of whether that screen is a phone or a massive television.
So it's all percentages.
Exactly.
And our notes mention specific typographical units that act this way too, right? EM and ORM. What is the physical mechanism behind those?
They are brilliant solutions for scalable reading. EM is a unit inherited from traditional print typography. It historically represented the physical width of the capital letter M in a specific font.
Okay.
In web development, one EM is a relative multiplier based on the font size of its immediate parent container.
Oh, I see. Meaning, if the main box has a font size set to, say, 16 pixels,
Right.
and I tell the headline inside it to be 2 EM, the browser does the math and renders the headline at 32 pixels.
Exactly. It scales proportionally. And then you have REM, which stands for root EM.
How is that different?
Instead of looking at its immediate parent box, REM always calculates its size based on the single foundational root font size of the entire HTML document,
Why does that matter?
because it is critical for accessibility.
Oh, right.
If a visually impaired user alters their browser settings to enforce a massive root font size so they can read, a site built with REMs will perfectly scale every single element, image, and menu proportionally without breaking the layout.
Wow. That mathematical fluidity is incredible.
It's very smart.
But, what happens when things just physically don't fit?
What do you mean?
Let's say I have a complex sidebar with 30 navigation links. On a big desktop monitor, it looks great on the left side.
Sure.
But on a phone, it takes up the entire screen and completely covers the article I'm trying to read. Percentages can't fix that, can they?
No, percentages just make it a slightly smaller obstruction in that case.
Right.
For structural transformations like that, responsive design relies on a technology called CSS media queries.
A media query.
Mhm.
It sounds like the code is interrogating the device.
That is exactly what it is doing. Media queries are logical IF statements built directly into the design code.
Okay.
Our source text gives a fantastic example of a class called MenuLateral Aside Menu.
Right.
The developer can write a media query that states, if the screen currently viewing this page is narrower than 360 pixels, locate the side menu and set its display property to none.
Boom. The code detects the narrow phone screen, and the menu just vanishes, replaced by, like, a tiny clickable hamburger icon.
Exactly. But if you take that exact same phone and rotate it horizontally into landscape mode, the screen suddenly becomes wider than 360 pixels.
Oh. And the media query instantly detects the change in width.
Yes. It recalculates, and the side menu automatically reappears on the screen. The layout literally responds to the physical orientation of the hardware in real time.
That is so cool. This fluid power completely inverted how designers think, didn't it?
Oh, completely.
Our sources specifically contrast the old philosophy of graceful degradation with the modern standard of mobile first. Let's talk about that.
Graceful degradation was basically a symptom of the desktop era.
Right.
A design team would sit at their massive monitors and build the ultimate, feature-rich, wildly complex website.
The dream version.
Right? And then as an afterthought, they would try to cram it onto a phone. They would progressively strip features away, degrading the experience until it barely functioned on a small screen.
And it usually felt like a broken, compromised experience for the mobile user.
It really did. But today, global internet traffic is overwhelmingly mobile. The desktop is actually the secondary device now.
Wow.
So the industry adopted mobile first, which is also known as progressive enhancement.
You completely flip the script.
Exactly.
You start with a blank canvas the size of a smartphone screen. Because space is at an absolute premium, you are forced to make hard decisions right away.
Right. You have to decide what the absolute core, essential purpose of this application actually is.
So you build the leanest, fastest, most critical version of the interface first.
Yes. And then, as the screen size increases to a tablet or a desktop, you progressively enhance the experience.
Ah, I see.
You add the high-resolution background video, you add the complex multi-column layouts, you add all the intricate hover effects. You scale up from a really strong foundation rather than trying to tear down a bloated mansion.
Okay, so we know the philosophy is fluidity. We know the goal is a seamless user interface.
Right.
But what are the actual tools the browser uses to execute this? Let's dive into the client-side toolkit.
Yes. We are looking at the holy trinity of front-end development. The three languages that every modern web browser inherently understands: HTML, CSS, and JavaScript.
The source material uses a really brilliant construction analogy to explain how these three distinct technologies collaborate.
I love this analogy.
Let's elevate it a bit. Imagine you are building a custom home. First, you need a plot of land.
Right.
In our digital world, the plot of land is the server. It is the physical space where the project lives.
Okay.
Now, the very first thing the construction crew does is pour the concrete foundation and erect the wooden beams and load-bearing pillars. That structural skeleton is HTML.
Hypertext markup language.
Exactly.
HTML provides the structural and semantic meaning to the raw data. It honestly does not care about aesthetics at all.
Right.
It uses tags to define the reality of a piece of content. Like, is this blocker text a primary header? Is it a subheader? Is it a hyperlink? Is it an image?
But if you looked at a website built strictly with HTML, it would be hideous.
Oh, it would look like a document from 1993.
Exactly. Black Times New Roman text aligned to the far left on a blinding white background.
Right. Because nobody wants to live in a house that is just exposed wooden beams and raw concrete.
No.
You need an interior designer. You need drywall, paint, elegant hardwood floors, architectural lighting.
And in the browser, that aesthetic layer is CSS.
The cascading style sheets.
Right.
CSS is a declarative language entirely dedicated to visual presentation. It reaches into the HTML skeleton and applies rules.
Okay.
It says, take all the primary headers, change their font to Helvetica, make them dark blue, and center them. Take this image, round its corners, and float it to the right.
But why keep them separate, though? Like, why not just have one single language that builds the wall and paints it at the exact same time?
Ah, the separation of concerns. This is a massive principle in computer science.
Oh, really?
Yes. By keeping the structural content, the HTML, entirely segregated from the visual design, the CSS, you achieve incredible flexibility.
How so?
A company can completely rebrand their entire website, changing every color, every font, the entire layout,
Yeah.
simply by swapping out one single CSS file,
Oh, wow.
without ever having to touch or rewrite the thousands of pages of underlying HTML content.
That is incredibly efficient.
It is.
Okay, so we have the beams, which is HTML, and the paint, which is CSS. Our house looks beautiful,
Right.
but it is completely dead. There is no running water, the light switches don't work, the front door is locked.
Right.
To make the house actually functional, you need electricity and plumbing.
Right.
And that brings us to the third language, JavaScript.
JavaScript is the behavior layer. It is a wildly powerful multi-paradigm programming language that executes directly inside the user's browser.
Using the CPU power of the client's own device.
Exactly.
Yeah.
HTML and CSS are static. They
Yeah.
just sit there. JavaScript is alive. It can think, calculate, and make decisions in real time.
And the mechanism it uses to interact with the page is called the DOM, right? The Document Object Model.
Yes, the DOM.
How does the DOM actually work?
Well, when your browser receives the HTML from the server, it reads it and constructs this sort of mental hierarchical map of the page.
Like a family tree.
Exactly, a massive family tree of every single element. That tree is the DOM. JavaScript acts like a master electrician holding the blueprints to that tree.
Okay.
It can traverse that tree instantly and alter it on the fly.
So when I type my password into a form and I get a little red text popping up saying password must contain a number before I even click submit,
That is JavaScript.
it intercepted my typing, ran a logical check, and reached into the DOM to inject that red warning text instantly without ever talking to the server.
Yes, it handles all the immediate local interactivity.
Yeah.
But before we move on, we really must highlight a major structural upgrade mentioned in our notes, HTML5.
Oh, right.
The evolution of HTML itself actually solves some of the most critical vulnerabilities on the web.
I remember the dark days before HTML5. If you wanted to watch a video or play an interactive game or see a complex animation, HTML just couldn't handle it.
Not natively, no.
You had to download and install third-party plugins, like Adobe Flash.
Which was an absolute disaster.
Oh, it was awful.
Flash was notorious for consuming massive amounts of battery, crashing browsers constantly, and basically acting as a massive backdoor for security vulnerabilities.
So HTML5 fixed that.
Yes. It eliminated the need for plugins entirely by introducing native multimedia tags. Developers can just type video or audio, and the browser inherently knew how to play a movie right out of the box.
That's huge.
It also introduced semantic tags. Instead of using generic div-id footer containers for everything, HTML5 introduced actual descriptive tags like footer, article, and nav.
Why does that matter?
This isn't just about clean code. It is a profound accessibility upgrade.
Oh.
Screen readers used by visually impaired users can now seamlessly identify the navigation menu versus the main article content, vastly improving the usability of the web.
That's incredible.
HTML5 even allowed web pages to cache data locally, meaning a website could partially function even if the client lost their internet connection.
Amazing. All right, so JavaScript is the electricity, but if I can stretch this house analogy to its absolute breaking point,
Let's do it.
how does JavaScript keep the lights on and the TV playing while the house is actively being renovated?
Oh.
That brings us to one of the most important concepts in modern web architecture, the illusion of speed and the magic of the asynchronous web.
To understand why this is magic,
Yeah.
we have to remember the deep frustration of the synchronous web.
The early 2000s internet.
Yes. Let's say you are filling out a massive multi-page job application online. You spend 20 minutes typing, you get to the bottom, you take a deep breath, and you click Submit Next Page.
And then the entire browser just freezes.
The white screen of death.
You can't scroll, you can't click anything else. You just stare at a blank screen for 5, maybe 10 seconds.
Right.
And if the server encountered an error, the entire page reloaded, wiping out your 20 minutes of typing.
It was awful. That is a synchronous request. The communication happens in a single blocking sequence.
The client is blocked.
The client sends the HTTP request to the server, and then the client completely paralyzes its own interface until the server responds. It is a highly inefficient use of the user's time.
So the solution was to stop freezing the interface, the shift to asynchronous requests.
In an asynchronous model, JavaScript handles the communication in the background.
Okay.
When you click a button, JavaScript fires the HTTP request to the server, but it essentially says, I'm not going to wait around for you. Call me when you have the data.
Oh, nice.
It leaves the connection open, but allows the user to continue scrolling, clicking, and interacting with the rest of the page.
The technology that brought this to the mainstream is called AJX, right? Asynchronous JavaScript and XML.
Yes.
Think about how you use a social media feed today. You are scrolling down, looking at photos. When you reach the bottom of the feed, the page doesn't suddenly freeze, turn white, and reload to show you more photos.
Instead, you experience infinite scrolling. As your screen approaches the bottom of the page, JavaScript fires an asynchronous AJAX request to the server behind the scenes. It asks for 10 more photos.
And then
The server sends them back, and JavaScript seamlessly injects them into the DOM at the bottom of your screen. Your scrolling is never interrupted. The interface feels completely fluid, just like a native app.
our sources dive into the specific mechanics of traditional AJX. It relies heavily on a built-in JavaScript object called XML HTTP request.
It does.
And there's a really fascinating detail here about how the browser handles human psychology while it waits for the data.
Yes, the ready state property.
Right.
When XML HTTP request opens a background conversation with a server, it constantly updates a status number. Status 0 means unsent. Status 1 means opened.
Okay.
But status 3 is the critical one. Status 3 means loading processing.
And the reason status 3 matters is because that is the exact trigger for the loading spinner.
Exactly.
When the code hits status 3, the developer writes a script that says, okay, the server's thinking, so display an animated GIF of a spinning wheel.
It is a profound psychological trick.
It really is.
Human beings absolutely hate waiting in the dark. A frozen screen makes us think the system is broken, and we panic and hit refresh.
Which just overloads the server even more.
Exactly. But if we see a tiny spinning wheel or a little skeleton outline of the content shimmering, we feel acknowledged. We feel like the machine is working hard on our behalf.
The animation basically buys the server precious seconds of patience.
Yes. And when the request hits status 4, which means done, JavaScript immediately deletes the spinner and injects the text.
I love that. The loading spinner isn't just a byproduct of a slow system. It's a deliberately engineered pacifier tied to a specific JavaScript status code.
It's all psychology.
But the notes also mention that XML HTTP request is an older standard, and there's a newer way to do this now.
Right. The modern standard is the Fetch API.
Okay.
Conceptually, it achieves the exact same background asynchronous communication, but it utilizes a modern programming architecture called promises.
A promise. That sounds very poetic for computer science.
It is surprisingly literal, actually. A promise is a JavaScript object that represents the eventual completion or failure of an asynchronous operation.
Okay.
Instead of writing incredibly complex nested callback functions that turn into impossible spaghetti code, a developer can write clean, linear code.
How does it read?
They essentially say, fetch this data. Then, when the promise is fulfilled, display it. Catch any errors if the promise is broken.
That is so much cleaner. The notes also pair fetch with something called service workers, and this seems like the ultimate safety net.
Service workers are remarkable. They are scripts that run on the client's machine, but they run entirely in the background, completely divorced from the web page itself.
What do?
They act as an incredibly intelligent proxy server sitting right inside your browser.
Okay, so how does a proxy inside my browser actually help me?
Well, imagine you are reading an article on a train, and you go into a tunnel. You completely lose your cellular connection.
Yeah.
You click the link for the next page. Normally, the browser would try to send the HTTP request, fail, and show you the little dinosaur no internet screen.
Right.
But a service worker intercepts the request before it even tries to leave the phone. It said, we are offline. Let me check my hidden local cache.
Oh.
If it downloaded that page earlier, the service worker instantly serves it to the browser. The user clicks a link while entirely offline, and the page loads instantly. It makes the web incredibly resilient.
Okay, we have thoroughly explored the dining room at this point.
We have.
We know the menu is HTML, the interior design is CSS, the waiters taking our orders are JavaScript, and they use AJAX to bring us extra bread without pausing the entire dinner service.
Great analogy.
Now, it is time to push through those swinging doors. Let's go into the kitchen. We are diving into Section 7, behind the curtain, the server side, and databases.
To understand the modern server, we must first distinguish between the two types of web pages, static and dynamic.
In the early 90s, the web was almost exclusively static.
It was.
It operated like a global filing cabinet. If you visited a university's homepage, the server physically possessed a text file on its hard drive called index.html.
When the web server received your HTTP request, it simply picked up that exact file, put it in an envelope, and mailed it back to you.
Right.
The crucial limitation of a static web is that everyone in the world who requested that URL received the exact same file. It was essentially just a digital brochure.
But the internet we use today is profoundly dynamic. Think about logging into your bank account. I go to bank.com and I see my checking balance and my name.
Right.
You go to the exact same bank.com, but you see your balance and your name. The server isn't handing us a pre-written file.
No, it's not.
It is physically building a unique custom web page from scratch just for me in the millisecond after I ask for it.
Exactly. To assemble a custom page on the fly like that, a server needs computational power. It needs a factory.
And in our source material, the head chef running this factory is a server-side programming language called PHP.
PHP. It's been around forever, and it powers massive chunks of the web, including WordPress.
But how does it actually interface with the user?
It doesn't.
Wait, what?
And that is the most important architectural security concept to grasp here. PHP runs exclusively on the server. The client never touches it.
Okay, let's trace the life cycle of a login attempt to see this factory in motion.
Let's do it.
I type my username, Bob, and my password into an HTML form on my screen. I click Submit.
The browser packages Bob and the password into an HTTP request and sends it to the web server.
Okay.
The web server looks at the request and says, this isn't a static HTML file. This requires thinking. So it hands the data over to the PHP interpreter.
PHP wakes up, it takes the data. What does it do next?
PHP connects to the database vault in the back room. It runs a query. Does the username Bob exist? Does his password match?
And the database checks.
The database says yes and hands PHP Bob's account balance.
Yeah.
PHP then acts as an assembly line. It takes an empty HTML template, injects Bob's name and balance into the correct P tags, and generates a brand new finished HTML document.
And here is the magic trick. PHP then hands that finished raw HTML document back to the web server to send to the client. The PHP script then terminates.
Exactly. When Bob's phone receives the response, all Bob sees plain HTML. P, welcome back, Bob. Balance, $100 P.
That's it.
Bob has absolutely zero idea that the server just executed 50 lines of complex PHP logic, verified cryptographic password hashes, and queried a database to generate that one sentence.
Wow.
The actual source code of the application is completely invisible and impenetrable from the outside.
That opaque wall really protects the proprietary logic of the company.
It does.
Oh, wait, I want to back up a second. We sort of glossed over how my password actually traveled from the browser to the server.
Yes.
Our text highlights a massive security distinction in how HTML forms send data, specifically the difference between the GET method and the POS method.
This is a critical mechanical difference. When a developer builds an HTML form, they must specify an action, which is where to send the data, and a method, which is how to transport it.
Let's say I'm on a shoe store website. I use the search bar to look for sneakers. The developer probably used the DET method for that search form. How does GET transport the word sneakers?
The DET method literally takes the data you typed and appends it directly to the end of the URL in your browser's address bar.
So the URL suddenly changes to shoestore.com search.query sneakers.
Yes. The data travels out in the open, fully visible in the web address.
That seems fine for a search.
It is. This is fantastic for searchability and sharing. You can copy that exact URL, text it to a friend, and when they click it, their browser will send the exact same GET request, and they'll see the exact same search results.
But imagine the sheer disaster if a developer used the GET method for a banking login form.
It would be a catastrophic security breach. If you typed in your credentials, the URL would become bank.com/SUGTH or Baba password super secret 123.
Oh my God. Anyone standing behind you could see your password right on the screen.
Worse than that, that exact URL with your password in plain text is now permanently saved in your browser history, stored on the router's logs at the coffee shop you're in, and saved in the server's access logs.
Which is why developers absolutely must use the POST method for any sensitive, destructive, or just large amounts of data.
Correct.
How does PST actually hide it?
It doesn't put the data in the URL. Instead, the browser securely encrypts the data and tucks it deep inside the hidden body of the HTTP request packet.
So the URL just says bank.com/login.
Exactly. The data travels invisibly behind the scenes.
Okay, so the encrypted PST request arrives at the server. How does our chef, PHP, actually reach out and catch that invisible data?
PHP uses specialized built-in global variables called superglobals.
Superglobals.
They are essentially holding arrays that automatically catch incoming data. If the form used the DSHE method, PHP automatically populates an array called GOT. If the form used POST, PHP catches the data in an array called POST.
Our sources actually provide a specific code snippet from W3 Schools that perfectly illustrates this mechanism. It's a great example because it bridges the Brazilian origin of our notes with, universal code.
Let's roleplay it.
Okay. I am the user. I see a simple form asking for my name and email. The developer has set the form method to POST. I type in the name Jose Oliveira and the email joseoliveira@xpteo.com.br. I hit submit.
The browser packages Jose's details into the body of an HTTP POST request and fires it to the server. The web server receives it and wakes up the PHP interpreter.
Inside the PHP script, the developer has written code to reach into the superglobal array.
Exactly. The code essentially says, create a new local memory variable called nome. Now look inside the POPAT array for a field labeled name, extract the data, and store it in nome.
And it repeats the process for the email.
Right.
So now the PHP server holds Jose Oliveira in its active memory.
Yes. And the next line of code is an output command. The developer writes echo welcome nome.
PHP executes the command. It concatenates the text welcome with the variable data Jose Oliveira, generates the final HTML sentence, and sends only that HTML back to Jose's browser. The cycle is completely finished.
It is an incredibly elegant system, but it highlights one massive vulnerability.
What's that?
PHP has amnesia.
Yes. PHP is a stateless execution environment. The second it finishes sending the HTML back to Jose, the script dies, and its active memory is completely wiped.
So if Jose comes back tomorrow and tries to log in, PHP has no idea who he is, forgot his name, his email, his password.
For a system to be useful, it needs long-term memory. It needs a vault.
And this brings us to the absolute foundation of the architecture.
Yeah.
The SGBD.
Yeah.
The database management system.
Our notes highlight two absolute heavyweights in the open source database world, MySQL and PostgreSQL. These aren't just simple text files, are they?
No, absolutely not. These are relational database management systems.
Yeah.
Think of them as incredibly advanced, highly secure, deeply interconnected arrays of spreadsheets. They store massive amounts of data in tables with rows and columns, and they maintain strict logical relationships between different tables.
So they're robust.
They are heavy-duty pieces of standalone software that run constantly on their own dedicated channels on the server, known as ports.
Ports are like designated receiving docks, right?
Yes.
The web server listens on port 80 for regular HTTP traffic, but the database hides in the back. PostgreSQL listens on port 5432. MySQL listens on port 3306.
Exactly. Traffic intended for the database bypasses the web server entirely and goes straight to the correct dock.
A perfect analogy. Now, we have a logistical problem. PHP needs to talk to the database to check Jose's password.
Right.
But databases speak their own specific language, SQL structured query language.
They do.
Furthermore, MySQL speaks a slightly different dialect of SQL than PostgreSQL does.
Yes.
I can see where this is going. If a developer spends 6 months writing thousands of lines of PHP code that speaks the specific MySQL dialect perfectly, what happens if the company gets bought out? And the new parent company demands they switch their entire infrastructure to PostgreSQL.
Historically, the developer would cry.
Literally.
They would have to manually comb through thousands of files, locate every single database query, and rewrite it into the new dialect. It was a massive, expensive nightmare.
So how did the architecture evolve to solve the nightmare of switching databases?
By introducing an abstraction layer. In PHP, this life-saving technology is called PDO, PHP Data Objects.
It acts as a universal translator.
Exactly. PDO sits right in the middle. The developer stops writing code tailored to MySQL. Instead, they write their PHP code using PDO's standardized universal syntax.
Okay.
When the application starts up, the developer simply tells PDO which driver to use.
So they write one line of code that says, "Hey PDO, please load the MySQL driver." PDO takes the universal commands from PHP, seamlessly translates them into the MySQL dialect, and talks to the database.
And if the company forces a switch to PostgreSQL tomorrow, the developer doesn't rewrite the application.
They just change that one single line of code to say, "Hey PDO, load the PostgreSQL driver instead."
The abstraction layer handles all the complex translation under the hood. It saved countless hours of human labor.
That is the epitome of smart engineering. And once PDO establishes that solid connection, PHP can finally execute the 4 fundamental commands of data manipulation. Our sources refer to them by the acronym CRED.
The foundational pillars of almost every application on Earth. Create, read, update, and delete.
It sounds so simple, but when you think about it, almost everything we do online is a CRED operation.
Signing up for an Instagram account, that's a create operation.
Right.
Scrolling through your feed, that is a massive read operation. Changing your profile picture, an update. Taking down an old embarrassing post, a delete.
The complexity of the modern web is really just those 4 basic database operations wrapped in beautiful, responsive CSS, animated by asynchronous JavaScript, transmitted via HTTP, and orchestrated by a server-side language like PHP.
It is breathtaking when you step back and look at the entire assembly line.
It is a profoundly complex symphony, engineered entirely to feel effortless to the user.
Absolutely.
Let's do a quick recap to anchor all this. We started by defining the relationship. The client initiates the request, the server processes and responds.
Right. We trace the history from the centralized freezing mainframe rooms to the distributed multi-tiered architecture that protects our data and allows massive scaling.
We explored the rigid, stateless rules of HTTP and how push notifications invert those rules to save battery life.
We examined the physical challenges of interface design, moving from rigid adaptive layouts to the fluid, percentage-based math of responsive design, driven by the mobile-first philosophy.
We looked at the toolkit, HTML building the structure, CSS painting the walls, and JavaScript manipulating the DOM to bring the page to life.
We saw how AJAX and the modern Fetch API broke the paralysis of synchronous loading, using background requests and clever psychology, like the Status 3 loading spinner, to keep the user engaged.
And finally, we pulled back the curtain on the server. We saw how PHP acts as a secure, invisible factory, catching POST requests, utilizing the PDO translator to talk to massive relational databases, and dynamically assembling raw HTML to send back to the client.
It's a lot, but it all works perfectly together.
So you now know exactly what happens in the milliseconds after you click a link. But before we wrap up, our expert has one final, highly provocative thought for you to ponder.
I do.
Something that takes everything we've just learned and turns it slightly sideways.
So throughout this entire deep dive, we have drawn a very hard, strict boundary between what is a client and what is a server.
Right. The client consumes, the server provides.
But technology doesn't stand still. Our source text notes a quiz question where one of the incorrect answers claims the client-server model is becoming obsolete because of the Internet of Things, or IoT. But if we extrapolate into the near future, is that statement actually wrong?
That's a fascinating question. The lines are definitely blurring.
Think about the Internet of Things. Think about a high-end smart fridge in your kitchen.
Okay.
On one hand, it is absolutely a client. It reaches out to a weather API in the cloud acting as a client to download tomorrow's forecast and display it on the door.
Right. It's requesting data from a server. Classic client behavior.
But let's say you are at the grocery store. You open an app on your smartphone, and you tap a button to view a live camera feed from inside your fridge to see if you need to buy milk.
Wait, in that exact scenario, my smartphone is the client. It is making the HTTP request.
And your refrigerator receives the request, processes it, retrieves the live video data from its internal camera, and pushes the response out over the internet to your phone.
Oh, wow.
In that millisecond, your kitchen appliance is acting as a fully functioning server.
Wow. So it is both. It switches roles depending on the specific transaction.
Exactly. As we move toward a hyperconnected mesh network, the strict hierarchy established in the 1970s is dissolving.
It's basically obsolete.
Any device with a microchip and an IP address could potentially serve data, and any device could consume it. The clear distinction between the dining room and the kitchen is disappearing.
That's wild.
We are moving towards an architecture where everyone is both a patron and a chef.
That completely reframes how I look at the devices around me. So the next time you are sitting in your living room and you look at your smart TV, your thermostat, your phone, or your watch,
Yeah.
I want you to ask yourself, in this exact moment, are you the client or are you the server?
Or perhaps wonderfully, you are both.
Well, that is all the time we have for today. We started this journey looking at the crisp white tablecloths of the digital restaurant, assuming the internet was just seamless magic.
And now you know the recipe.
You know the kitchen staff. You know exactly the incredible choreography happening behind those swinging doors. Thank you so much for joining us on this deep dive, and we encourage you to keep exploring the invisible conversations happening all around you.